Hello everyone. In this video we're going to continue our discussion of mathematical reasoning. So previously we've talked about two types of reasoning, inductive and deductive. So see if you remember the difference between these two types. Alright, inductive, this one starts with specific pieces of information, things like examples, and then from there reasons to a general conclusion. So it's observing patterns and trying to predict what will be true in general in all situations. Deductive reasoning, on the other hand, already starts with one of these previously accepted statements, and then it moves on and applies it in specific situations. Alright, so an example of inductive reasoning, let's say that every day you go to work and your boss is wearing a red shirt. Alright, so this happens for 3 months straight, and it's a little weird, but you start to get the impression that this boss just really likes red shirts, and so your prediction is that your boss will always be wearing a red shirt. Alright, so then you might expect the next day to also see your boss wearing a red shirt. Right? And that may or may not be true, but that process of looking at those specific examples of days and seeing the red shirts, okay, then that led you to some sort of a conjecture. This is true all the time. Now, deductive reasoning, sometimes we'll pick up where inductive reasoning leaves off. All right, so if we are able then to, to prove in some case that conclusion is true all the time, then we could use it and go on to make other statements. All right, so let's say that you figure out, you read the employee handbook and you see that, well, actually, the boss is required to wear red shirts as part of the uniform. Right, so then that would prove that your conjecture is correct. Right, it didn't use inductive reasoning to prove it. It used deductive. All right. And here's kind of where we picked up, right? The generally accepted statements that we're then using to prove that conjecture were the fact that the employee handbook is true and that those are accepted rules or laws for that workplace. And then we could apply that in this specific situation to say, okay, well then yes, the boss is always going to wear a red shirt. All right, if the inductive reasoning was, led to something that was not true, right, then what we would need to do to try to disprove this pattern or type of reasoning would be to find a specific example that contradicts the conjecture. So to find a counterexample, you try to think of an example that meets all of the conditions of the conjecture, but for which the conclusion is false. Right. So let's say that you inductively decided that the name in English of every month contains either the letter Y or the letter R. So maybe really quickly you just thought, okay, January, February, March. Oh, those all have Y's and R's in them, so this is your conjecture. Well, now to disprove this, what we have to do is think of an example that meets the conditions of this statement. It has to be the name in English of a month. Those are the conditions. And then it has to contradict the conclusion. So the conclusion was that if it is one of these names of a month, then it contains Y or R. So this is the conclusion. Conclusion, all right. And what we need to do is contradict this. Now there's a fun math symbol for a contradiction. This can save you some time. It's looks like this, and this is dueling swords, right? So they're kind of like at an impasse in the duel there, and that means that we've found a contradiction. All right, so what we just need to do is just think of an example. All right, so think of a month that does not contain the letter Y or the letter R. All right, so maybe you can come up with some of those. Let's see, I think June would work, and August. And I think that's it, right? So we only need one of those to disprove this statement, but in this case we actually have two different ones. All right, how about this statement? If we're trying to decide whether or not this is true, all numbers that are divisible by 5 are also divisible by 10. All right, is this true or false? So if we think it's false, then we need to come up with an example that proves that, a counterexample. So we need it to meet the conditions of the conjecture. It needs to be divisible by 5, okay? But then it needs to contradict this one. It needs to not be divisible by 10. All right, so think of a number that is divisible by 5 that's not divisible by 10. Okay. Quick review, divisible means the number divides it evenly. Okay, so like 12 is not divisible by 5. 5 doesn't go into it evenly. So a number like 25 would be a good counterexample. This is divisible by 5, but it's not divisible by 10. Something that would not work. All right, this one is not a counterexample. The number 20. All right, so some people will switch these, and they'll try to look for something that that is divisible by 10 and then maybe not divisible by 5, or some people will just get confused and skip over this first part entirely. All right, but it's always agreeing with the first part, contradicting the second part. All right, try this one. You might want to pause and try this on your own. All prime numbers are odd. Okay, so we need to think of a prime number that's not odd. Okay, or in other words, an even prime number. All right, do you remember what prime numbers are? Prime numbers are any numbers whose only factors, only positive factors, are the number 1 and whatever the number is itself. All right, so 5 is prime because its only factors would be a 1 and a 5. Okay, so can you think of one? A prime number that is even. Right, in this case, we only have one possibility for a counterexample. The only prime number that's not odd is the number 2. All right, but it still proves that the statement is false. Okay, let's do an example of these two types of reasoning working together. All right, little number games like this, all right, where you are given some instructions and then somebody can guess at your answer, or you notice that it's, it magically works out to be the same thing every time. All right, so let's see what we have here. Think of a number, multiply it by 2, add 6, then divide by 2, and then subtract your original number and see what the result is. Okay, so let's try this. We'll try a few examples first. All right, so this is inductive reasoning. We're going to start here. Okay, so you can try this process. I'll try this with the number 3. All right, so I'm going to multiply it by 2, add 6, and then divide by 2, and I get the number 6. Okay, if we try it with 5, multiply it by 2, add 6, divide the result by 2. Oh, subtract the original number. I forgot that step. Okay, so then subtracting, we get 3, and subtracting, we get 3. Okay, how about, okay, we can do 10. Multiply by 2, add 6, divide by 2, subtract the original number. All right. So at this point, maybe you see a pattern here. Maybe you have a conjecture about what the answer is. In all 3 cases, I have gotten the number 3 as an answer. Right, maybe you did too in yours. So let's use deductive reasoning to try to prove that this is true. All right, well, how are we going to do this? We can't check every single number, and we also only looked here, at least the ones that I've done, have been what we call natural numbers or counting numbers. Right, they're positive and they're whole, no fractions, no decimals. But the problem just said to think of a number. So, would this still work if we started with 1/2 or negative pi? All right, so we certainly don't want to test all of those weird cases, especially when we get into the division and things. That could be kind of tedious. So instead, we can use algebra to prove this. Well, what could we use to stand for any number at all? Right, how about the letter x? All right? So you start with an x as your number, and then you just use algebra and arithmetic to follow through and complete all of those different instructions for x. So we multiply it by 2, and you might remember we write that as 2x. Add 6, 2x plus 6. Okay. These are not like terms, so we can't add those together. But then when we divide by 2, we divide both of those things. So 2x divided by 2 is x, and 6 divided by 2 is 3. And then we subtract the original number. Well, in this case, we used x to represent our original number, so we're subtracting x. And then x minus x, that's 0. And we're left with 3. All right? So this is deductive reasoning. We have proved this. We haven't assumed anything about x. We just used a letter. Right? It could have been 1/2. It could have been -4. So we've proved that no matter what you start with, you always get 3 as the answer. Okay, try this one. Think of a number, add 2, multiply by 12, divide by 3, subtract 8, and then divide by 4 and see what you get. Okay. So I'll start with 3 again, add 2, multiply by 12, divide by 3, subtract 8, divide by 4. Okay. Let's try 5. Add 2, multiply by 12, divide by 3. Let's see. That's 28. Subtract 8, divide by 4. Okay, you might want to try this and see what you think the conjecture is, what the pattern is. All right. Well, I noticed I started with 3 and ended with 3. Started with 5, ended with 5. So maybe we always end with what we started with. All right. So let's try to prove this. And again, pause and try this on your own if you like. But we'll start with x. All right. Then add 2. Then multiply by 12. And you might remember we have to use the distributive property. We want to multiply the x and the 2 by 12. So that gives 12x plus 24. Okay, and then divide by 3. So we divide each of those things. So 12x divided by 3 is 4x. And 24 divided by 3 is 8. Then we want to subtract 8. So we've got plus 8, then minus 8. It's going to give 4x. And finally divide by 4. So 4x divided by 4 is just going to be x. All right, so again, we've used algebra to solve. Just work out the arithmetic in each step. And we see that starting with x always gives x as the answer. All right, so no matter what you start with, you'll get the same number as a result. So you might notice in those examples, we observed patterns to make predictions. The patterns were trying it with different numbers. Right? Making the prediction was the guess about what the pattern was and what would happen, what we would end up with. That's inductive reasoning. And then we used rules and laws from algebra, things like how to work with variables, right? The distributive property, things like that, to prove those patterns. Right? So that's deductive reasoning because we used previously accepted laws and rules and facts from algebra. All right, so this is an example of a logical argument, and we always start out with premises and then we reason to a conclusion. Right? So premises can be assumptions, laws, rules, widely held ideas, or observations. And then we reason either inductively or deductively from the premises to reach a conclusion. All right, so for example, if you start with an observation and you reason from there to get to your conclusion, then that's inductive reasoning. That's starting with an example, an observation, a pattern, something like that. But if you're starting with a law, a rule, a widely held idea, or even an assumption, okay? So like little sayings that people assume to be true. All right, so let's see. I'm trying to think of one. Like the love of money is the root of all evil. Okay, and maybe somebody doesn't believe that, but they're just going to assume that that's true because a lot of people say it. All right, something like that. All right, then if you're starting with any of these things and then reasoning to your conclusion, that's going to be deductive reasoning. All right, so we're taking these things as truth and then reasoning from there to basically applying those widely held ideas or laws, applying them in specific situations to make little small conclusions about other things. All right, so let's look at a couple examples, try to identify the premise and the conclusion, and then based on what type of premise it is, decide whether it's inductive or deductive reasoning. All right, so how about the last 6 times we played our arch rival in football, we won, so I know we're going to win on Saturday. All right, so first thing we need to do is divide this up and figure out which piece is the premise and which piece is the conclusion. All right, so look for things that say so or then, little keywords in the middle here. That's going to indicate kind of a break, right? So the part that comes before it is the premise, and if you're labeling these on your own, you might want to just use like a P and a C, something like that. All right, so that's the premise, and then so I know we're going to win on Saturday. That's going to be the conclusion. Okay, so we're starting with given information. The last 6 times we played our arch rival in football, we won. So think about what that is. Is that a law, a rule, a fact, an observation, an example? And that is an observation. Okay, those are specifics. We're talking about 6 specific games. And then we're reasoning from there to what's going to happen on Saturday. All right. Now we're going to say that this is reasoning to in something that happens in general, right? Or kind of, if you want to think of this as like a prediction. Okay, sometimes the specific to general thing is a little bit vague. So think of this as a prediction about what happens in the future, what happens next, all right? Or in general, in all situations, or in this one, in the next situation. All right, so that is inductive reasoning. How about there is no mail delivery on holidays? Tomorrow is Thanksgiving, so I know my student loan check won't be delivered. All right, so let's divide this up. We have to figure out which piece is the premise, which piece is the conclusion. All right, so I see the keyword so. All right, so this person's reasoning based on the previous facts, then or so they know something else. So this first part is the premise, and we actually have 2 premises here. We have 2 statements. There's no mail delivery on holidays, and tomorrow is Thanksgiving. And then here's the conclusion. All right, so what is this? Well, let's start with no mail delivery on holidays. Okay, that is a general statement. It's talking about all holidays, and it's stating this as a true accepted fact that there is no mail delivery on holidays. Okay, then tomorrow is Thanksgiving. It's a little more specific, so sometimes that can be confusing. It looks like we're starting with specific information, but what we mean by specific is like a single example or something that doesn't happen all of the time. Whereas this is still a proven, known fact, right? And it's kind of like a helper premise, right? It's supporting this one and saying, okay, here's our general rule, no mail delivery on holidays. Then because tomorrow is Thanksgiving, I know that I can apply that general rule to tomorrow, and I can apply that rule to say, okay, then I know that my loan check won't be delivered. All right? So we're still working from we could call this a law or a rule, and then we're applying it to a specific situation. Tomorrow, the student loan check, that's a type of mail, and it won't be delivered. Oops. One situation. All right, how about all vegetables are purple? Lettuce is a vegetable, so we know that lettuce is purple. Okay, this one is ridiculous. Doesn't really make sense, but this is set up as a logical argument. It begins with two premises. All vegetables are purple, lettuce is a vegetable. So, we reason to this other conclusion that lettuce is purple. Okay, premise, conclusion. All right. So we're being presented with this statement, all vegetables are purple, as a generally accepted true statement. Now, of course, it's not true, but if we're taking this as our assumption or our widely held idea, all right, that is a general statement. It's made about all vegetables, and it's saying that, yes, they are purple. Okay, then lettuce is a vegetable, so we can apply that to this specific situation and know that lettuce is purple. So this is deductive reasoning. Even though it's false, it's still a valid type of reasoning. Okay. Okay, the next one. I own an orange fish. My friend owns an orange fish. Therefore, all fish are orange. Okay. Therefore is another key word that lets you know that what comes next is a conclusion. Right, so this is the conclusion, and this part is, these are the premises. All right, so look at your premises. I own an orange fish. My friend owns an orange fish. All right, and think about what they are. And those are specifics. They are examples or observations in just two small cases. Your fish, your friend's fish. And then we're reasoning to this and saying, okay, well then, whoa, let's apply those little examples to a giant situation. We'll generalize it and say that all fish are orange. Right? So it's kind of going the opposite way from it. Deductive, this is inductive. It's looking at specifics and assuming that they're going to be true in every situation. All right, so that concludes our discussion of this topic, inductive and deductive reasoning. So see if you can do these things. Explain the difference between inductive and deductive reasoning. Identify premises and conclusions. So we kind of marked up statements or arguments. Okay, we marked them, premises, conclusions, labeled them. We classified reasoning as inductive or deductive based on what type of premise we had. We used inductive reasoning to make reasonable conjectures, right? Looking at a pattern. We did some with numbers or figures, right? And tried to decide what came next. We made reasonable conjectures. We didn't know that they were true, but it was a best guess. And if a conjecture happened to be false, we should be able to disprove them now using counterexamples. And in just a few cases, you should be able to use deductive reasoning to prove a conjecture to be true. So we did the algebraic examples, starting with x, and then you reasoned to different things. We had one that ended with x, or x ends in 3, something like that. All right, that's it. Thank you for watching.